x, and then that whole thing is squared. And sometimes we write it like this. In fact, most of the times we write it like this. The reason we put the 2 in front of the x to represent the function sine of x times sine of x or sine of x squared is if I put the 2 over here, we might get it confused as sine of x squared as opposed to sine of x squared. So that's why we write it that way, but it means the same thing. So we're asked to verify algebraically that this is periodic and determine its period graphically. Now it's kind of confusing. I'm not quite sure I always agree with how the book does this because at the end of the day, I got to make sure that you guys understand what periodic is because that's the main objective here. So let's talk about what periodic is. Periodic is where there's a pattern that occurs that repeats itself. So first and foremost, let's graph it and take a look at it. And so let me clear out. Got a whole bunch. In fact, I think I have that. No, I guess I don't. And so let's graph it and look at it. So periodic means that we're going to have a pattern that repeats itself quite a bit. So when I square it, I get this kind of pattern that repeats itself. Okay? And so let's explain what periodic means, and then I'll do the algebra stuff. These are circular functions and they're composites of circular functions. And so what's taking place is, in the xy plane, as we rotate around the circle, as you can see, as we rotate around, depending on what angle we have, whatever the angle is, whatever that angle is, if I keep rotating around the circle, I'm going to have several points, and the points will start to repeat. When it repeats, we call it a period. Now, for every one of these points, we could draw a right triangle. If I drop the right triangle back down to the x-axis. And because we have a right triangle, I can have 3 sides of that right triangle if this is my angle theta, where this is the opposite and this is the adjacent. Now, when we use y and x, we do it just a little different with regards to how we consider. We could think of the angle x, but we still have an opposite, and we still have an adjacent, and we still have a hypotenuse. And so the red curve will be just sine of x. And what happens when I square something, it becomes positive. So if I have -1 and I square that, it becomes positive. Does that make sense?
Yes.
And so all these little negative regions, like right here,
those simply just get flipped up to the positive values because we're squaring. It grows a little different too, but as you can see, it pretty much looks the same. Okay? And so, how can I determine that that's periodic? Well, it says algebraically, and so I'm going to write down what the book says. To determine that it's periodic, we have to verify, and I'll explain why. I'm going to do the verification first. So if I have f of x is equal to sine of x, and then I square this whole thing. If it's periodic, we have to assume or guess what we think the period would be. Since sine of x is a function that is periodic, and it has a period of 2 pi, then we can assume that if I say like f of x plus 2 pi, right? And think about the unit circle, right? It doesn't matter where I end up on the unit circle. So for example, let's say I've got my little triangle here, and I have my perfectly drawn circle. But if I'm right here, and this is my angle, and I go 2 pi from that point, where do I end up?
Right back there.
Right back there. So if I come around 2 pi, that's 1 full revolution, right? So that's like x plus 2 pi. So if I write x plus 2 pi, I should end up at the same value, right? So what I did though is I replaced x with x plus 2 pi. So wherever I have that, I have to do the same on the other side. So now I'm going to have sine of x plus 2 pi squared. Okay? Does that make sense so far? So wherever there's an x, I replace with x plus 2 pi. So then what we've got to do is think that through a little bit. Well, sine of x plus 2 pi, because the period of sine is 2 pi, we know that this will be the same as this value here. We can think of this value corresponds to x or x plus 2 pi. So it's the same as sine of x. And isn't that what we started off with? So we say that it's periodic because with some period that divides by 2 pi, and then the other way to verify is by the graph itself. So that's the main thing, because I think the graphs are going to be easier for you than the algebraic verification. And so let me make some changes on my screen. Let me turn off sine for a second. Can you guys go ahead and grab your calculators out? Get those out and graph sine of, and I'm gonna enter this in just a little different. We're gonna say sine of x, and then we're gonna square it.
You did 2.
Then the next thing I want to do is we're gonna hit table set. So I hit second, then I hit window, and what I want to do is I want to start with 0, and then I want my table to be pi divided by 3, or my increment, my delta x in this case. So I'm going to choose that value, and then I'm simply going to go, actually I'll do pi divided by 6. So I'm going to say pi divided by 6.
Why
now
not 3?
Huh?
Why not 3?
Pi divided by 3 would be fine, but I want it to be kind of, what this is going to do is in my table of values, we're going to start off with 0, then we're going to do pi over 6, then we're going to do 2 pi over 6, 3 pi over 6, and it'll convert it as a decimal. Remember, pi over 6 is the same as 30 degrees, so we're going to get the values every 30 degrees in the table of values. Pi divided by any number would work. You could do pi divided by 10, but I'm going to stick to values that we kind of know. Okay, so now once I've done that, I'm going to hit second graph, which gives me my table. And remember that the first graph is the one that we're interested in. And so you can tell it's periodic by looking at the values. I have 0, 0.25, 0.75, 1, 0.75, 0.25. And notice that it repeats. When do we get 0 again?
3.14.
What do you think that is?
Should be 3.
Yeah, it's 1.59, but rounds up to 1/6. So that's pi, isn't it?
Yeah.
So what would you say the period is?
Pi.
Pi.